Title: Mastering Algorithm Efficiency, the Worst Case Scenario. Today, we are going to study one of the most important concepts in algorithm analysis: worst case analysis. Whenever we develop software, we naturally ask questions such as: how long will this algorithm take to execute? Will it remain efficient if the amount of data increases? Can users rely on it during peak workloads? To answer these questions, computer scientists analyze algorithms mathematically instead of simply measuring execution time on a particular computer. Among all methods of performance evaluation, worst-case analysis is the most widely used because it provides a guaranteed upper limit on an algorithm's execution time. Imagine you are designing software for an air traffic control system. Hundreds of aircraft may be approaching simultaneously. In such a situation, hoping that the software receives easy inputs is not acceptable. The software must remain reliable even under the most demanding conditions. Similarly, consider an online banking application. During salary days or festive sales, millions of users may access the system simultaneously. If the underlying algorithms perform poorly under heavy loads, transactions may fail, causing financial losses and poor customer experience. Worst-case analysis prepares us for these challenging situations. Rather than asking how fast can the algorithm run, it asks a more practical question. What is the maximum amount of work this algorithm may ever need to perform? Title: The Hidden Cost of Code. At first glance, a program appears to be a collection of simple instructions. However, every instruction executed by the processor consumes computational resources. The first concept on this slide is no fixed speed. Many beginners assume that an algorithm always runs at the same speed. In reality, the execution time of an algorithm depends on several factors, including the size of the input, the arrangement of the input data, the efficiency of the algorithm, and the hardware on which it executes. For example, a sorting algorithm may finish almost instantly when sorting 10 numbers, but the same algorithm may require several minutes or even hours when sorting millions of records. The second concept is input sensitivity. Consider linear search. If the element we are searching for happens to be the first element in the list, the algorithm terminates immediately after one comparison. However, if the element is the last item or does not exist at all, every element must be examined. Although the algorithm remains exactly the same, the execution time changes dramatically depending on the input. The third concept is objective metrics. Since execution time depends on hardware, operating systems, and programming languages, measuring seconds or milliseconds does not provide a fair comparison. Instead, computer scientists count the number of elementary operations, such as comparisons, assignments, and arithmetic calculations. This mathematical approach allows us to compare algorithms objectively, regardless of where they are executed. Therefore, the hidden cost of code is not measured by clock time, but by the number of Title: The Performance Triad. To fully understand an algorithm, we analyze its behavior under three different scenarios. Together, these form the performance triad. Best case. The best case represents the most favorable situation. It measures the minimum number of operations required for an input of size n. For example, in linear search, if the required element is found in the first position, only one comparison is necessary. Although this gives us the fastest possible execution time, it is often unrealistic because it depends on exceptionally favorable input. Average case. The average case estimates the expected performance over many random inputs. Instead of assuming perfect or worst inputs, it predicts what usually happens in practice. For example, if the search target is equally likely to appear anywhere in the list, linear search examines approximately half the elements before finding it. Average case analysis often reflects real-world performance, but calculating it requires knowledge of input probability distributions, making it mathematically more complex. Worst case. The worst case measures the maximum number of operations required for any valid input. For linear search, this occurs when the target is absent or located at the very end of the list. In this situation, every element must be examined. Title: Why Worst Case Wins. Now let us understand why worst case analysis has become the standard in computer science. The first reason is guaranteed upper bound. Worst case complexity tells us that the algorithm will never perform worse than a certain limit. For example, if we say that an algorithm has a worst-case complexity of O(n log n), we guarantee that even under the most difficult input conditions, its running time will never grow faster than this rate. This guarantee is essential when designing dependable software. The second reason is critical systems safety. Consider applications such as medical monitoring systems, autonomous vehicles, aircraft navigation, nuclear power plants, financial trading platforms. In these systems, delays can have serious consequences. Engineers cannot design such systems assuming ideal inputs. They must prepare for the most demanding situations. Worst-case analysis ensures predictable performance even under extreme conditions. The third reason is mathematical simplicity. Surprisingly, determining the worst-case input is often easier than calculating the average case performance. Average case analysis requires probability theory and assumptions about input. Title: Defining complexity. Having understood why worst-case analysis is important, let us now define computational complexity. Complexity measures the number of elementary operations performed by an algorithm as a function of the input size, represented by n. Instead of writing execution time in seconds, we write a mathematical function called Tn. For example, Tn is equal to 3n plus 5. This expression tells us that as the input size increases, the number of operations also increases. The value 3n represents operations repeated for each input element. The constant 5 represents fixed initialization work. Notice that Tn is independent of processor speed. Whether the algorithm runs on a laptop, workstation, or cloud server, its mathematical growth remains unchanged. Now compare two algorithms solving the same problem. Algorithm A performs approximately Tn is equal to n superscript 2. Algorithm B performs Tn is equal to n log n. For small datasets, the difference may appear insignificant. Title: Asymptotic notation, the measuring tape. To compare algorithms consistently, computer scientists use asymptotic notation. Think of asymptotic notation as a measuring tape for algorithm growth. The first notation is big O, written as O(f(n). Big O describes the upper bound, meaning the algorithm will never perform worse than this growth rate. It is primarily used for worst-case analysis. The second notation is big omega, written as omega(f(n). Big omega describes the lower bound. It tells us the minimum amount of work the algorithm must always perform. The third notation is big theta, represented as theta(f(n). Theta indicates a tight bound, meaning both the upper and lower bounds are the same. In other words, Theta precisely describes the algorithm's growth. These three notations allow us to compare algorithms mathematically without worrying about programming languages or hardware. They form the universal language of algorithm analysis. Title: The Growth Hierarchy. Not all algorithms grow at the same rate. Understanding growth rates is essential because small differences become enormous as input size increases. At the top is O1, or constant time. No matter how large the input becomes, the execution time remains approximately the same. Examples include accessing an array element by index or retrieving a value from a hash table. Next is O, log n, logarithmic time. Binary search belongs here. With every comparison, half of the remaining search space is discarded. This makes logarithmic algorithms extremely efficient. Then comes O, n, linear time. Algorithms such as linear search examine every element once. Execution time increases proportionally with input size. Finally, we have O, n superscript 2, quadratic time. Nested loops commonly produce quadratic complexity. Examples include bubble sort and selection sort. For small datasets, quadratic algorithms are acceptable. However, as input size grows, their performance deteriorates rapidly. This hierarchy reminds us that selecting the correct algorithm is often far more important than upgrading hardware. Title: Danger Zone: When Things Get Ugly. Some computational problems become so difficult that even the fastest computers cannot solve them efficiently. Polynomial time algorithms, such as O n superscript 2 or O n superscript 3, are generally considered practical. Although they may become slow for very large datasets, they remain manageable for many applications. However, exponential algorithms, such as O2, are entirely different. Each additional input element doubles the amount of work required. Suppose solving a problem with 30 elements takes 1 second. Increasing the input to 31 elements doubles the computation. By the time we reach 100 elements, the required execution time may exceed the age of the universe. Problems such as the traveling salesman problem, Boolean satisfiability, and many combinatorial optimization problems exhibit this explosive growth. When exact algorithms become impractical, computer scientists often use heuristics, approximation algorithms, or meta-heuristic techniques such as genetic algorithms and simulated annealing. Under title: Real-World Impact, Sorting and Searching. This slide demonstrates how complexity directly affects real-world software. Consider sequential search. Its worst-case complexity is O(n). If the desired element is absent, every record must be examined. This approach is simple but does not scale well for very large datasets. Now consider insertion sort. For nearly sorted data, insertion sort performs remarkably well. However, for randomly ordered data, its worst-case complexity becomes O(n superscript 2). When sorting millions of records, quadratic growth becomes extremely expensive. Modern software therefore prefers algorithms such as merge sort or quick sort, which generally achieve O(n log n complexity. Choosing an efficient algorithm can reduce execution time from hours to seconds. This demonstrates that algorithm selection has a far greater impact. Title: The Architect's Takeaway. As we conclude today's lecture, let us reflect on the most important lessons. First, design for the worst case. Never assume users will always provide favorable inputs. Robust software anticipates the most demanding scenarios and performs reliably under pressure. Second, treat big O as a contract. When we state that an algorithm has complexity O, n log n, we communicate a performance guarantee to every future developer, researcher, and user. Finally, remember that scalability is not an optional feature, it is a fundamental design requirement. Software systems often begin with a few hundred users but eventually serve millions. Algorithms that scale efficiently enable this growth without requiring complete redesign. The most successful software engineers are not those who merely write code that works. They are the ones who design algorithms that continue to work efficiently as the world